Greetings and welcome to the introduction to astronomy. In this lecture, we are going to talk about light and its nature and the electromagnetic spectrum, different types of light and what we mean by light. So what is light? Well, light is a form of electromagnetic radiation. And this is created by charged particles which are moving. Now, light, when I say light, you tend to think of visible light, what you see with your eyes. However, true light is actually a lot more than this. It is not just the light that we see. There are lots of other types of electromagnetic radiation. And as you see this here, visible light is only a tiny portion here of the entire electromagnetic spectrum. So we also have longer wavelengths like radio waves, microwaves and infrared, and shorter wavelengths like ultraviolet, X-ray and gamma rays. But these are all electromagnetic radiation and are light, just like visible light. So what is light a little more? Is light a wave or a particle? And this is very interesting because light actually has uh, properties of both. So let's look at the wave nature of light first. Well, light is a wave which is characterized by a wavelength and a frequency. And for any wave, the velocity of the wave is equal to its wavelength, which is given by the Greek letter lambda, times the frequency. So if you know the velocity and you know either wavelength or frequency, you can calculate the other. For light, this is a constant. This is c. This is the speed of light, which is 300,000 kilometers per second. So when we look at the properties of a wave here, we see the wavelength, the distance from crest to crest, or from trough to trough. It's exactly the same, or actually from any point to the same point. If we looked here to here, that would all be, each of those would be a wavelength. The frequency would be how many of these waves pass you every second. So if a frequency of 10 would be 10 waves per second, 10 waves passing you every single second. Now, what are some of the properties where light acts like a wave? Light undergoes interference. So we see interference patterns in light, much as we see in a wave pool, where waves can combine together to give you very large waves or cancel to give you no wave. We see reflection, refraction and diffraction among waves. And we also see the Doppler effect, which we will talk about in a future lecture. So light does behave in many ways like a wave, but it also behaves like a particle. In this case, we have the particle is known as a photon. And the energy of that photon is given by a constant multiplied by the frequency. So a high frequency light like X-rays then has a higher energy than a low frequency light like radio waves. And even within the visible portion, a very high frequency visible light would be violet, would have more energy than a low frequency light like red. Now, how does light act like a particle? Well, one thing is the photoelectric effect. And that is that light behaves like a particle, in that if you need a certain amount of energy, you need that specific energy to eject an electron from a metal. So you can send all of the red light in here that you want, and it will not eject any electrons. Once you hit that critical energy, you now have enough energy to remove that electron from the metal. And how fast it moves depends on the amount of energy. But if you don't have enough, you do not have enough. It doesn't matter. It's not that they'll add together. They are individual particles. So you cannot just put billions of red light waves and expect that it would eject electrons. So one violet photon would be sufficient to eject an electron. A billion red photons would not. Light also undergoes gravitational deflection, and we'll look at that in future lectures as well. So let's look at the electromagnetic spectrum, how we can split up this light. We looked at this a little bit already, and we'll come back to this when we talk about telescopes. But there's different types of energy depending different types of light depending on their energy and their wavelength. So longer wavelength is radio waves, and longer wavelength means lower energy. Shorter wavelength, higher energy. And what we look at with which ones we can see from the ground, well, we can see visible light makes it through our atmosphere, as do radio waves. But that's about it. Most of the rest of the electromagnetic spectrum cannot get through our atmosphere. So that's why we tend to be biased towards optical, because that's what we can see, because it gets through our atmosphere. If we want to study things like X-rays, gamma rays, ultraviolet, etc., we need to get up above the atmosphere, or at least most of the atmosphere, to be able to see that. So as long as we're in the atmosphere, and until we were able to get satellites up into orbit, these types of energies from space we were not able to see. Now, we can also look at this in a table form. So we see them here, and we see what are the wavelengths. This will give you the range of wavelengths in nanometers. A nanometer is a billionth of a meter. So from very long wavelengths, many meters for radio waves, to very short wavelengths, less than 1/100th of a nanometer. What kind of objects radiate these? Well, it depends on the temperatures. So these are low temperatures down here that radiate radio waves, and high temperature objects give off gamma rays. It takes a lot of energy to give off the high energy particles. So when we're looking at cool objects, cold gas and things, we'll get a lot of radio waves. Visible light is stars and galaxies, and high energy processes like the X-rays in supernova remnants and clusters, we will see very much X-rays, and even into some gamma rays in some very high energy situations. Now, we also want to talk a little bit of an aside and talk about temperature here, because we need to look at that, and we want to use that to understand our radiation laws, which are coming up. So what is temperature? Well, temperature is a measure of the average kinetic energy of particles. And we can measure that in multiple different scales. The United States uses the Fahrenheit scale. In science, mostly is the Celsius scale often used. In astronomy, we use the Kelvin scale more often. And that is the scale that is based on the absolute zero. There is a lowest possible temperature that you can get. And that's because the temperature is the measuring the velocity of the particles, their average energy of motion. So if the particles were to stop moving, theoretically, you would reach absolute zero. That is the lowest temperature you can get. And in the Kelvin scale, absolute zero is 0 Kelvin. That is it. You cannot get any colder than that. There are no negatives in the Kelvin scale. So when we talk about things like temperatures of stars, we often will refer to them in the Kelvin scale. But there are other scales that are used as well. Now let's go ahead and look at those radiation laws and see what we have here. First of all, we want to talk about black body radiation. These are ideal radiators. And essentially what a black body does is it absorbs all the light that strikes its surface, and then re-emits light dependent only on the surface temperature. So an example of a black body would be something that appears very dark. It's not reflecting any light. So it's hard to see here on Earth. It's at its low temperature, it would be emitting primarily infrared light. So our eyes would not be sensitive to it. So you would be unable to see that light, but you could measure that it was giving off infrared light. An object like a star is also a decent approximation of a black body. It absorbs the light that strikes it, and it gives off light based on its temperature. So our sun isn't reflecting light, it is creating its own visible light. Now, the two laws we want to look at are the Stefan-Boltzmann law, which tells you that a higher temperature means you have a higher intensity at every single wavelength. So these curves here for 5,500 Kelvin, 4,400, 3,400, and 2,500, they never cross. So the 5,500 Kelvin star would be emitting its light primarily in the visible portion of the spectrum. A much cooler star would be emitting far more red light or even infrared light, but would still emit a little bit. So what would we see? If we looked at a star like one of these, they're emitting a lot of red light and very little blue and violet. So these are going to appear red to our eyes because they're emitting lots more red light. Another star might appear a yellowish white, and a very hot star might peak in the ultraviolet and might actually give off more blue light and look blue. The energy is equal to a constant times the fourth power of the temperature. So doubling the temperature of the star therefore means that you're going to have 16 times the amount of energy emitted. And this is why we get some of those extremely massive stars that are emitting lots and lots of energy. Now, the other one we want to look at is Wien's law. Wien's law says that a higher temperature means the wavelength is shorter at the peak. So let's look at that here in our chart. The peak at 2,500 degrees is way out in the infrared. At 3,400, it's getting closer to the visible. At 4,400, it's in the infrared. And at 5,500, it's right in the middle of the visible. So if you know the temperature, you take 3 million, divide it by the temperature, and that will give you the peak wavelength in nanometers. So we can use that as a way to calculate the maximum of the wavelength. So let's go ahead and finish up with our summary. And what we looked at was the electromagnetic spectrum, and it's more than just visible light. We looked at the dual nature of light and how it can behave as a wave and a particle. And we looked at the radiation laws that tell us how the spectrum can vary with temperature. So that concludes this lecture on light and the electromagnetic spectrum. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.